So I should probably say that it's not very clear to me what the composition of the audience is. So nothing that I'm going to say will be of particular interest for mathematicians or genuine mathematicians. So I've kind of pitched it at the level of my usual audience, which is holographers and string theorists with some interest in black holes and so on. So hopefully, and I've pitched it at a level which is sort of broad interest. So I hope that, was that a question? Sorry. Okay. So yeah, so this is, and also this is about some work that is kind of ongoing and about to appear hopefully sometime in the next month or two. So if you have any questions, comments, etc., we would it will help us out because it will kind of iron out the rough edges, so to speak. So, and my latest collaborators in this, Vaibhav and Pradeep are my students, and Suchethan is a postdoc who has joined us very recently. Yeah, I think that's basically the introductory slide. So my talk is about, there is some kind of an echo somewhere.
Yeah.
Okay. Yeah, so I think it's still there. Can you hear it? Oh no. Okay, now it's fine. Yeah. So but the talk is basically about the question of, fundamentally, it's about the question of horizons on black holes, and the nature of black hole horizon has been a source of confusion ever since the discovery / invention of the Schwarzschild metric. And this debate has gone through various iterations and has been revived in the context of the information paradox in the last decade or so. So, and I've listed some of the key papers in this, about the information paradox. Probably the one that I will have most to talk about is the last one towards the end. So, yeah, so this is the setting. And so I'll start by making a few comments about what, how I'm going to think about how I'm going to think about horizons. So in classical relativity, as we know, horizons necessarily have an entropy, and that's the crucial point in some sense, is that it is sort of unaccounted for entropy. There is no microscopic understanding of this entropy in classical relativity, and so the nature of the horizon is therefore intimately tied to the question of the existence of microstates for these horizons in the bulk gravitational description. So we kind of know from Strominger and Waffa and so on that we can account for this entropy in a holographic, in the microstates in string theory in some suitable sense. But what we really mean by understanding the horizon or understanding the information paradox is basically to understand that in the setting of the bulk directly. So that's how we will understand how Hawking's calculation is not leading to information paradox, let's say. So if the horizon is part of the description, there is no way to avoid having unaccounted entropy. So this is what I said. And so I would state that it means, sort of by definition of what a microstate means, that a microstate description cannot contain conventional horizons. Okay, so this is, I think it is not a controversial statement, but I don't know whether it is stated quite this way as regularly as I think it should be. So yeah, so essentially because a microstate by definition does not have any entropy in it. So, but I also want to make a distinction between, it may not necessarily mean that, so I'm not necessarily suggesting that the EFT description has to necessarily break down at horizon scales. But at the same time, I think it means that the previous statement that I made, that the UV complete description and the effective field theory description, effective field theory for me, it means, general relativity plus conventional quantum field theory in curved space kind of stuff. And so this, they should start departing at the horizon scale. So they should substantially depart from each other at the horizon scale. This, I think, is probably more of a controversial statement. I don't know, but I think it sort of necessarily follows from the previous slide, I would think. So this is sort of the premise of where I'm starting. So if you disagree with the statements in this slide, I think we can maybe pause for a second, or you can ask this eventually. So the statement is that, like, I expect that because microstates by definition cannot have any entropy, the conventional horizons cannot be part of the microstate description, or they should substantially deviate. And it also means by essentially, so it means that the effective field theory, since effective field theory means general relativity plus standard quantum field theory, if it is well defined within the interior, it should probably differ from the UV complete description in some substantive way starting at the horizon. So yeah, so this is the statement. So yeah, so a crude way to explore this possibility is to declare that black holes have no interior in the UV complete description. Okay, so this is what this was first done. There are various iterations of it, and I'll kind of walk you through some of the history of this, sort of the physicist version of the history of it. I don't know whether it's chronologically completely accurate, so yeah, so the first person, as far as I know, who thought about the possibility of chopping things off at the horizon and doing abject violation of the principle of equivalence was Toft in 1984, where he considered the possibility that you can you consider the scalar field essentially around the black hole background, a fixed black hole background, but instead of looking at a smooth horizon, he considered the possibility that there is a brick wall right before the horizon, and then he essentially uses a Bohr-Sommerfeld kind of quantization to sort of indirectly count the modes that are trapped between the brick wall and the angular momentum barrier in the Schwarzschild scalar field potential. So this is essentially his calculation, and so I will elaborate it a little bit more maybe a little bit later. So this is what he does essentially. So it is crucial that he did this calculation indirectly. He doesn't actually compute these modes. He has an indirect argument using this semi-classical Bohr-Sommerfeld kind of count. And essentially what he is counting are the modes that are trapped behind the horizon. And because it's semi-classical, which means that there is, in some sense, he's only looking at the modes that are trapped there. There is no, he's not really taking into account of tunneling in a straightforward way, at least. So tunneling across the angular momentum barrier. So this fixes the entropy. So if you do that, and if you fix the brick wall at a Planck length away from the horizon, in geodesic distance away from the horizon, you find that the area is proportional to, the entropy is proportional to A by G. The order one number he was not able to fix. And that is essentially the calculation that he did. This is surprising because it's, you got an area law out of what seemed to be sort of an extensive calculation of the modes in some region of space-time. So for instance, if you did this calculation in standard flat space with some walls and stuff, what you would end up finding is that if you count the number of modes inside it, you would basically get Planck's result, which is extensive in volume, but here instead you've got an area law. So that's what is sort of surprising about this calculation, and it's usually attributed to entropy, so to entanglement entropy across the horizon and things like that. Okay, so that's the setup. Can you hear me, by the way? Because if I can't see you because I'm using an old laptop. So
yeah, I can hear you. I can hear you.
Okay. So just interrupt me at any point.
Yeah, everything's fine. Yeah.
All right, good. So so that's the basic introduction to this whole stretched horizon. Or Toft called it brick wall, but I think it was renamed by Susskind as stretched horizon, and the name has stuck. So the stretched horizon or the brick wall also serves as a basis for the arguments in one of the sort of the first papers. I mean, maybe the first paper on black hole complementarity, which is basically the idea that somebody who falls through the horizon should see a smooth interior, even quantum mechanically. And this paper, the reason I mentioned that is because that paper has the title Stretched Horizon and Black Hole Complementarity. So, but gradually, so this is in the 90s, early 90s, I'm not exactly sure which year, but over time, the stretched horizon has kind of become a persona non grata at some level. And it's generally viewed as some sort of crutch rather than an actual physical entity. So, so this may or may not be correct, and I'm not necessarily, so we are going to explore it, but I'm not going to make, so let's see what happens. So, so that's the sort of the first iteration of the stretched horizon in the 80s and 90s. But in the 2000s, after the ADS-CFT correspondence, so to speak, the fuzzball program initiated by Lunin and Mathur and Bena and Warner and many other people came up as, I would call it sort of like, at least philosophically, an avatar of the stretched horizon idea. So the only difference is that it is constructed in supergravity, which descends from string theory. And it's the interesting thing for me in the fuzzball setup is that it sort of shows that string theory has mechanisms in it that can allow you to evade no-hair theorems. That's really what I sort of take away from it. And people take much more things from it, and opinion is sort of divided, I guess. So but this fact, I think, is certainly true, which is that in the stringy setting, we can evade no-hair theorems by you can have the same charges as a black hole asymptotically, but at the same time have structure near the horizon and not have a horizon. So in some sense, it also suggests the same picture, that black hole microstates only have the exterior of the black hole and not the interior. So I should also say that this opinion is very definitely divided about the status of fuzzballs in string theory. And so there are strong arguments, I would say, for believing that the spherically symmetric let me not get into it because it's not very important for me. But there are symmetry based arguments to argue that microstates of spherically symmetric black holes, they should actually be spherically symmetric themselves, but it's typically the constructions in fuzzball program typically are not of that kind. So this is considered to be sort of a weakness of the fuzzball program. So all of this is sort of like this at the level of story and background, so that I feel like I have to kind of defend thinking about the stretched horizon. So, and that's the reason I'm talking about this. And so the latest iteration of this this pro stretched horizon kind of an idea is that so the latest iteration of it is that as I'm sure you're familiar, some of you are familiar, is that there is a recent observation by Leutheusser and Liu that in holographic gauge theories in the large n limit, so there is a sector of the theory which is called the single trace sector, and the single trace sector you can think of as capturing the fluctuations around a fixed background in holographic gauge theories, fixed gravitational background in holographic gauge theories. And so the observation of Leutheusser and Liu is that in the large n limit, the single trace sector becomes a type 3-1 von Neumann algebra. So I think some people in the audience might know better than me what a type 3-1 von Neumann algebra is. But the thing that I want to emphasize is that at finite n, the single trace sector generates the entire CFTs, entire operators in the CFT, in the holographic CFT. But at infinite n, there is the single trace sector becomes type 3-1. And the interesting thing about the type 3-1 algebra for our purposes is that it necessarily has a non-trivial commutant. So let me show you a picture of an eternal black hole here. So this is an eternal ADS black hole. Ignore all this infowlers and things like that. So the thing that matters is that in an eternal black hole, you have a left side and a right side, and both sides are supposed to be dual to two different CFTs, or two copies of the same CFT. And the idea is that in the large n limit, so in the large n limit, the idea that the type 3-1 algebra has a commutant is basically the statement that there is naturally room for the left wedge of the eternal black hole. So that's the way in which one can think about this. So that means, so if you have the left and right wedge, of course you can construct operators in the interior. So that's what makes this interesting. So yes, so the commutant of the fact that in the large n limit there is a natural commutant that emerges is in that sense interesting. And what is even more interesting, or at least from the point of view of my talk, what is interesting is that if in a bulk language, so one could take the point of view that at finite n, since the algebra of operators in the exterior is type 1, or in the the CFT is type 1, if this, if I'm taking a quote from Witten's paper on cross products. If in the bulk language one could describe the algebra of observables exterior to a black hole as an algebra of type 1, because which is what you expect from a full CFT, the black hole information problem would very likely be solved. So so this seems to me like kind of a suggestion that a UV complete bulk description, if it exists, there may not be a black hole interior in that description. I mean, of course, you could have like instead of having a phase transition at infinite n, you could have
Hi, Chethan. Hi, can you hear me?
he actually does not compute
But he got out. Okay, so okay.
Yeah, he seems like off, like seems like cut off, and his internet. I don't know. He's trying to connect it, but it's not. He's not able to connect, I think. Oh man. Let's see. Yeah, you see, like, he's saying that he's connecting to audio, but it's actually not connecting. Yeah.
Did he respond to your email?
Two motivations for computing normal modes directly, and the reason is that one of them is to do with the fact that Hawking temperature and mass were both put in by
Chethan,
in order to.
your screen was not shared.
Oh, I see. Okay, let me just share it again. God. I think it should be coming up now. Is it? Can you see it?
Yes, everything good. Yeah.
Okay, great. Okay, so I was just mentioning that so in Toff's original calculation, he uses both the temperature of Hawking temperature as well as the mass of the black hole as inputs for computing the entropy. And this is something that one would like to avoid if you want to give it a genuine statistical mechanics kind of interpretation, because an ensemble is specified by either the mass or the temperature, and not you don't typically need both. And the second reason is that it kind of makes the area law, the emergence of the area law, a little bit mysterious. And one may hope that it is whether we can get some intuition for the origin of the area law by understanding the normal mode calculation. As I said, in the case of Planck's calculation, for instance, it's essentially the Planck calculation, but done near the horizon of a black hole. That's what Toft is doing. Of course, because the modes are more complicated because of the non-trivial shape of the potential and so on, it's a more technically involved calculation, but conceptually it's very similar. So if we want to interpret the black hole entropy as a entanglement entropy, it will be interesting to kind of connect it with this sort of more mechanical, more dumb kind of way of doing this. And that's one other reason why it's interesting to look at it. Okay, so yeah, so what we'll do is we'll try to compute normal modes as opposed to quasi-normal modes for black hole stressed horizons. And quasi-normal modes correspond to the boundary conditions that are infalling at the horizon. And these normal modes, of course, depend on the actual physical cutoff or which we are imposing for the field, let's say a scalar field at the stressed horizon. And that is usually we'll take it to be Planck length during this talk. So essentially our goal is to view this stressed horizon as a poor man's standard for a microstate of a black hole. But before we start, one thing we could do is try to see whether these normal modes capture some of the physics that is expected of black holes in general. And one of the things that has come up a lot in the recent past or in the last decade or so is the fact that black holes are scramblers. Black holes are highly chaotic systems. And so the question is, can we see the hint of chaos from these normal mode spectra? So this is generally considered to be somewhat unlikely for fuzzball microstates in general. So of course we are not going to do it in the context of fuzzballs, because generic fuzzballs are complicated beasts. But so we can again come up with a simple generalization of our scalar field model that we claim the stretched horizon is, by looking at to model a fuzzball by a profile which is angle dependent. So in the case of fuzzballs, they come with these arbitrary profile functions, which basically correspond to the freedom that you have in the microstate. So an analogous thing that one could do in the context of a scalar field would be that you you have at the stretched horizon, you have an angle dependent profile for the scalar field instead of just the usual Dirichlet boundary conditions. So this will be sort of the natural model for a toy model, if you like, of a fuzzball in the setting of just if you want to do this with the scalar field. So it's a slight generalization of what Toff did. And the point is that then you can compute the normal modes. And the thing that we find is that they pass basic diagnostics of a random matrix type system. So I'll just you don't have to know this.
Sorry, this is Maria. I have a question. You went a bit too quick. So what is okay. You mentioned that this chaos would not be, so what is the intuition that this would not realize for fastballs? And then if you can comment on, typically these normal modes are computed for objects that are stable. Do we know that the fastballs that you want to test are stable? Where are we with that?
Yeah, so for instance, I mean, that's the second one. I think let me address that for second one first, because I think that to the extent, so it's certainly true that, so I think that this calculation at the level of stability should I don't think I have a real defense for that. But what I would say is that for Schwarzschild black holes, where it's a question of whether, it's I really view it as sort of a toy model, right? I mean, the stretched horizon, we don't, in classical general relativity, we don't expect that a stretched horizon can be stable at all. So that's essentially the content of no-hair theorem. So when I put a cutoff right before the horizon, I've already sacrificed that at some level, right? So it is only in the sense of what can you learn from that is one, what I would say this calculation has any merit at all. So the things going for it are the things that I mentioned earlier, in the sense that if you let's say the fact that you can as you will see, you can see the entropy and temperature, etc., coming out sort of nicely. But I am certainly vulnerable to this question of whether what one should do. What should we take it as seriously as for instance a BPS microstate of a fuzzball, because which we know is necessarily, I mean, it has nonlinear instabilities, but it is not at least it is supersymmetry preserving and so on. So yeah, so that's the harder question. So what was your first question again? I forgot.
What you mentioned, we would not find out chaos for fastballs, or maybe I just got it. From the transition from one transparency to the other, you just mentioned that, and I was
so the general, so this is a statement that I've heard, for instance, Emil Martinez make. So let me so the general idea is that if you have a standing waves, right? So if you have ADS, for instance, like let's forget about fuzzballs for a second, and if it is global ADS, the standing waves would, roughly speaking, be evenly spaced. That's what one might expect. Okay, so and this is a reasonable expectation. So for instance, if you took flat space and put a hole in it, or ADS and put a hole in it, and then if you compute the standing waves of this system, you will find that the spectrum is, roughly speaking, evenly spaced. So you can think of it as roughly as a column of standing waves. And what actually happens is that even in the case of fuzzballs, what we find is that the level spacing in the principal quantum number is actually essentially evenly spaced. But what happens is that because of the angular quantum numbers have structure, and they are highly degenerate, and there is some interesting stuff that happens. And we have kind of diagnosed it, so to speak, to the existence of the redshift at the horizon. So anytime you have a redshift at the horizon and you put a cutoff, you would find these kinds of, some of the diagnostics of quantum chaos that people talk about, like, for instance, the spectral form factor having a linear ramp, or level spacing having the Wigner-Dyson form, and so on and so forth, that we will find that those things are essentially guaranteed if this thing happens. So the reason, I think, the motivation why people believe...
Let me just ask you. So for the cases that you're going to discussing, are you engaged, some gauge supergravities? Are you in ADS? Because all the statements for chaos are typically in ADS, as far as I can tell. And so I thought fastballs were not.
So I mean, so the what I'm working with is a stretched horizon. So I will work with a stretched horizon in a BTC setting. So BTC
Okay.
is, like you have
Yeah.
asymptotic radius, but so yeah. So but I think the question is, like the point is, I don't think I don't think I'm selling the statement that I want to make sufficiently well, because so I'm not trying to do the calculation in explicit first-ball geometries, because part of the reason is
Okay.
that the explicit first-ball geometries, the wave equations typically are horrendous, so you cannot really solve.
Okay.
I mean, the simple cases you can, but so I want to find a model which is sufficiently trivial, but hopefully not have thrown away the baby out of the bathwater, where I can, get some mileage with a simple model. So what I'm trying to do is I'm trying to solve a scalar field. So this is the setting in which Toft originally did his calculation. He took a Schwarzschild black hole, put a cutoff right before the horizon, and looked at the scalar field modes. It's a
Right.
probe scalar field. That's the
Okay.
setting in which. So the idea here. So this is what I was saying here, which is that I want to work with a scalar field with a profile at the stretched horizon, and I want to use it as a tractable toy model for a general first ball microstate. So this is sort of the, if you like, the philosophy. I mean, I agree with you 100% that it is, it's like a, it's an extremely bare bones version of what one would ideally like to do, but I think that
No,
it captures.
I am happy. I am happy with it's not that I'm against. I just wanted to understand.
Okay.
So
All
go
right. Thank you very
ahead.
much.
Go
Yeah,
ahead,
sure.
Chethan.
Yeah.
Thank you. Thank you for the clarifications. Go ahead.
Yeah, sure. Yeah. So what we are doing is basically that. Yeah. So as a model for this first ball generic microstate, what we are doing is we are treating the scalar field to have some kind of a profile at the stretched horizon, and then we try. Then we can solve the wave equation. It's you can solve the BTC wave equation with these boundary conditions, and it's a mess, but you can do it. And at the end, what you find is that you find some normal modes. You can explicitly compute them. So initially in these first papers, we were completely doing this numerically. So the advantage of BTC is that the wave equation, the solutions are hypergeometric. So at least the finding the radial part of the wave equation is sort of it can be done analytically, but at the final stage, when you actually want to evaluate the normal modes, it's one has to rely on numerics. At least that's what we did in these papers. So the spectral form factor, for those who have not seen it, I'll just flash a quick slide here, which is, it's kind of like a complexified partition function, the square of a complexified partition function. And the only reason why it is interesting is because if you have a linear ramp in the spectral form factor, as I'm sure many of you very well know, is then it is considered to be a diagnostic of some form of random matrix like behavior. So, and the thing is that the linearity of the ramp, and when I say linear ramp, I do mean the slope has to be 1. So you can find various ramp like structures which are not supposedly diagnostics of random matrix behavior, but having a slope 1 ramp is supposed to be a diagnostic of random matrix behavior. But of course, we have not really put in directly any random matrix in here. In fact, you would find the linear ramp even without putting any profile for phi naught. Even if you have phi equal to 0, you will find the linear ramp. So, and that's the slope of the ramp is 1. We have quite a bit of confidence in it at this point, because even we have some analytic results and so on. So that's one thing. So, and the second thing, which I will not explain much, is the second diagnostic is that of level repulsion. And level repulsion also you can see for these sort of arbitrary profiles. So if you don't know what level spacing distribution, etc., let me not get into it. It's not very important. It's just that it's another diagnostic, which can also, you can check that it works out for these toy fuzzballs, so to speak. So, I mean, I also want to emphasize that I'm not necessarily saying that these are necessarily robust indicators of chaos. I'm just saying that they capture some diagnostics of random, the standard diagnostics of random matrix behavior. So whether this is truly chaotic or not is, I don't really know. So, but the spectrum seems to capture some features of chaos. And I mean, it's, yeah. So I think that it's probably can exhibit chaos, but yeah, probably ultimately more work probably needs to be done. But it is interesting that with these simple-minded models that for trying to simulate fuzzballs, you can get both of these features that are supposed to be standard features of random matrix-like behavior. So that's that. So let me make a couple of comments about the general philosophy here. So the compact directions here are crucial. This translates to the fact that, what I mean by that is that these omegas, these normal modes are functions not just of n, but also of this j. So you can go to higher dimensions, then the j will have more components, but it's so there will always be these angular quantum numbers. So, and the crucial thing that gets this sort of done is the fact that the spectrum is exponentially denser in the j direction. So I will show you some plots of normal modes in a few slides. So the point is that, like, the expectation that the standing waves are roughly evenly spaced is true in the n direction, but in the j direction you have these it's not linear. It gets pulled down. So the spectrum in the j direction gets pulled down, and it's exponentially more degenerate than the degenerate, exponentially more closely spaced than the level spacing in the n direction. So that's directly responsible, as we will see, for the entropy and all those other things as well. So, and the third feature is that this seems to be a universal feature of horizons. For instance, we have tried it for various things, like various black holes at this point in some various detail. And ultimately, it all boils down to the fact that black holes near their horizon behave as linear space times some compact space. So, yeah, so, right. So let me give some contrast to how one should place this calculation in the landscape of all the ramps and random matrix stuff that I'm sure that you've heard in the last few years. So the ramp in the spectral form factor is usually thought of as the result of including replica wormholes in the, if you think of it as a gravity path integral kind of language, it's coming from it's a Euclidean calculation where there is an ensemble averaging involved and so on. And the result of, when you get that, usually it's a smooth ramp, because it's a Euclidean gravity calculation, there are no fluctuations. So, and this, for instance, can be explicitly calculated in 1+1 dimensional toy models of gravity, like JT gravity, which has implicit ensemble averages in them. So, but in true quantum gravity calculation, if you genuinely have a microstate and you do this calculation, you expect to find fluctuations, because there is nothing to smooth out these fluctuations. By fluctuations, I mean these fluctuations that you're seeing on top of the ramp. So if you did a JT gravity calculation, you would instead see a smooth ramp, which is, the microstructure of the black hole somehow doesn't seem to matter. But so this is, that's what you would expect. So, in a genuine microstate of quantum gravity, you would expect to see a ramp with fluctuations. And so by doing this really dumb thing of cutting it off with some fluctuations, with some profile around it, what we are seeing is that we can see both the ramp as well as the fluctuation, as long as there is a compact dimension. Okay, so, and this is, so in some sense, this sort of trivial calculation captures some aspect of quantum gravity, it looks like. Okay, so, yeah, so it'll be interesting to see if one can see more direct hints of chaos. And what I mean by that is something like, if you can you find something like eigenstate thermalization or something like that. So because typically, if you talk to statistical mechanics people, they tell you that if you can find, if you compute small operators in eigenstates of chaotic systems, they should thermalize. So with exponential suppression of the off-diagonal elements and so on and so forth. So, and that is something that we would like to actually see if possible, because that would be kind of the strongest indication that there is some kind of eigenstate thermalization happening, or a strong form of chaos. But this is hard because normal modes are hard to compute explicitly, first of all. And we can try taking a smaller step. So the first step that we will do is we will kind of, try to sharpen Toff's calculation by, instead of trying to, now we are kind of taking a step back from the chaos and just trying to see thermalization. By thermalization, I basically mean that, we can in principle try to compute expectation values of, let's say, 2-point functions in this, in the context of the stretched horizon for quantum field theory with the stretched horizon cut off near the horizon. And if you compute it, can you see, can we, in some limit or some approximation, can you get the Hartle-Hawking Green function? So Hartle-Hawking Green function is the green function that is associated to a smooth horizon, and it is thermal. So, and the advantage of having these explicit normal modes is that, so as I said, we initially were working with purely numerical normal modes, but for low-lying part of the spectrum, which is what is significant for Toff's calculation, we can also come up with analytic approximations. I'll show you one momentarily. So, but if you have such an some form of control on the normal modes, so we can also try to make sort of the most brutal approximation that one can make while retaining the success of Toff's entropy calculation. Because Toff's calculation is indirect, he doesn't have that much of a flexibility in how he can get the answer. So he gets what he gets. But because we have some understanding of what the normal modes look like, we can try to decipher what exactly is the feature of the normal modes that is responsible for giving us an area scaling of the entropy. So, so for doing this, we'll work mostly with the BTC black hole, because as I said, it's the wave equations, separate, and then you get these hypergeometric functions and so on. So, but so some of these arguments also generalize to other black holes in fairly simple ways. Not simple ways. It's fairly complicated ways. But at the end of the day, they kind of give you similar equations. So by making suitable approximations and so on and so forth. So yeah, so let me just show you one. I have not shown you any normal mode. I've just been telling you the story, and I'll continue doing that. But let me just show you the one explicit expression for the BTC normal mode here, which is, so if you look at this omega, it has two dependencies, n and j. J is the angular direction. And this n shows up only here. And RH is the horizon radius, L is the radius length. And Z0 is the location of the stretched horizon in tortoise coordinate. So at this, these numerical numbers that you see here are coming from some gamma functions, which have some numerical values and some limits and so on and so forth. So these are mathematical constants. And then the rest of the physics is captured by this log, which is, again, this J is the, so that the reason why the spectrum in the J direction is exponentially, closely spaced is because the N here shows up as N, but the J shows up as a log J. So that's really the reason. So, and so this is basically this is the base expression for the normal modes in the low-lying part of the spectrum, where which is what contributes to Toff's calculation. Okay, so and this approximation breaks down at some J max. As you can see, the denominator will become 0, but to get to the entropy, we don't need to go that high. So that's the real reason why this is actually a useful expression. And in fact, such an so you might think that, why are we putting a cutoff in J max? So essentially that comes from, in Toff's calculation, I don't fully understand the origin of the bound on J max, but in Toff's calculation, it shows up as a, essentially because he puts in a semi-classical approximation. So he wants to look at the semi-classical modes, which are, by semi-classical, these modes which are trapped between the barrier and the stretched horizon. So in that sense, there is some sort of an intuition for it, but it's still the precise way in which you get a bound in J is a little bit, tricky. But nonetheless, you can argue that there is a bound on J max. So the way we are going to do that is that I'll tell you exactly how we are going to fix the bound on J here. So let me just show you how these normal modes look like. So these two curves here correspond to this expression that I wrote down here for two values of n. And this is J, and this is n equal to 1 and 2, let's say. And this guy here is the exact normal mode. Okay, and the point is that for so this J is this is the place where the approximation breaks down, but it turns out that it's only like about 0.1 here, let's say, of, it's a very small fraction. I mean, this is for a fairly small, the cutoff is not sufficiently close to the horizon, so the J max is pretty low. So because I wanted to show you a plot which was kind of easy to show. So but on the other hand, if you have a J which is which means that the relevant part of the spectrum that contributes to the entropy and the temperature and all the thermodynamics and all that is basically happening around here. Okay, so that's this really low-lying part of the spectrum is what gives rise to all the thermodynamic features as we see. So yeah, so and this is the exact spectrum, and the reason why these lines look like they're continuous is because the J spacing, as I said, is exponentially small. Okay, so yeah, so the thing, so the next point I want to emphasize is that in order to do the success of Tove's calculation, we can simply assume. So if you notice here, so in this part of the spectrum, the J is, it's not like it's not completely degenerate, obviously, but you can see that the spectrum is, if you make the assumption that the spectrum is degenerate in J, in other words, you ignore this log J part, which for small j is only a minor correction, you find that the spectrum is like, it has some particular form, right? I mean, this J you just drop and then you find some expression, and that expression is linear in N, and it's completely degenerate in J. So it's not a particularly good approximation here. If you look at it, it's not terrible, but it's not great either. But the claim or the observation is that that's good enough to get you the result of Toft, which is basically that you have area scaling of the entropy. So if the J is degenerate and the N is linear, you already find an area scaling in the entropy. So in Toft's calculation, this is less clear, and there is, if you really try to determine it the way he did it, you will find that there is some complicated log corrections and so on and so forth, which are all fictitious. So if you actually look at the normal modes, they are not really there. So, but at the end of the day, this is the key ingredient that he needs in order to make the statement about the entropy. So of course, I mean, it's somewhat technical statement, and I'm not showing you enough expressions here. So, but nonetheless, I hope the basic idea is clear, that you can make a pretty crude approximation to the spectrum here in the low-lying part where Tove's calculation is done, and you can still reproduce the entropy. And the utility of that approximation is that it doesn't have this complicated log dependence on J, and it's completely linear in N. And you just ignore the J dependence, and that's good enough to get you the entropy. So this will be useful for us, because then, now that we know that that's all that is needed in order to get Tove's result, we can apply to some other calculation. So this is what we would try to do. So in particular, we would like to actually compute the 2-point correlation function in the stretched horizon setup, and try to see whether we can actually get thermal state as an approximation of the pure state correlation function. Okay, so what we will do is basically we will fix this J cut. So Toft had a semi-classicality argument for fixing this J, or implicitly fixing this J, and what we will do is we will demand that this J cut is chosen in such a way that the Bekenstein-Hawking entropy precisely gives us the A by 4G, including the coefficient, and not just the A by G structure with an order 1 unfixed coefficient. So by fixing that order 1 coefficient, we will fix the cutoff in J. And the interesting thing, or I mean, so as I said, so I don't fully understand even in Tove's calculation, I don't fully understand the origin of the cutoff in J, but so it is there that we can see. So in our case, we fix it by demanding that the entropy is precisely the A by 4G with the numerical coefficient correct. But the interesting thing is that once we do that, we also get the Hawking temperature exactly. Okay, so, and this in some ways, so we are able to basically fix the normal modes. Basically are helping you fix both the temperature and entropy in essentially what is a microcanonical setting, because we are fixing the mass of the black hole, and then this cutoff fixes the entropy and the temperature in one shot. Okay, so this can be viewed as sort of an improvement of Tove's calculation, if you like, because he needs to specify, as I said at the beginning of the talk, that he needs to specify 2 quantities, both the mass as well as the temperature, in order to fix the entropy. And even when he fixes the entropy, it's only fixed up to an order 1 number. Okay, so and so that's what that is. Okay, so the fact that we could drop the J dependence in the low-lying part of the spectrum and still reproduce the entropy suggests that we may be able to try to directly compute the thermal Hartle-Hawking correlate from a pure state calculation. So this is what so in the remaining few slides. So yeah, so I have a few minutes left. So so that's what I will kind of quickly outline for you. So so yeah, so note that the fact that this crude approximation is sufficient for Toft to get his entropy and temperature is crucial for this calculation that I'm mentioned here to work. Because if you knew the spectrum, and if it is some complicated spectrum, there is no way that we could do that. Because note that this is, when I say the spectrum, you have to kind of look at it from a Fock space kind of perspective, so that you can think of, the calculation. It's analogous to basically what one would do, as I said, in the case of Planck's calculation. So it is not just a single harmonic oscillator that you need the entire Fock space worth of them in order to actually reproduce this. So which means that with this, we'll have to, if you only knew the normal modes or some complicated hopeless expressions, then we would have no chance of doing this calculation. Okay, but because we can drop the J dependence in the part that is relevant for the thermal behavior, so we can, in principle, try to do a calculation which is essentially a harmonic oscillator calculation writ large, and hope to reproduce this 2-point function. So, and that's what we would do. So the claim is that, the claim that I want to make is that the 2-point function of a scalar field on a highly excited typical state, highly excited even eigenstate actually, so where the energy of the excitation is equal to the mass of the black hole on the stretched horizon vacuum, is equal to the Hartle-Hawking 2-point function plus up to corrections which are exponentially suppressed. So this is, it's a somewhat of a, there is some detail. Obviously, there are, details that I'm suppressing. But the point about this is that it can, in the case of BTC black hole, at least we can do all of these things in great detail. And there are some things about this calculation, as I said, I can tell you that at the end if you like, that some details of this calculation which I don't fully understand. And it has partly to do with Tove's assumption of semi-classicality. So I don't fully understand the connection between semi-classical modes versus the full, the genuine spectrum of the scalar field that we are working with. So it's a bit difficult because one of them is, like the tunneling information has gone into our calculation. So that's why it's a little bit unintuitive. So for instance, but the calculation, when you do it, it works out. So yeah, and this gives us sort of a general meaning to the oft-stated thing that, black holes, around the black hole, there is a thermal atmosphere. So, but I also want to emphasize this is not quite eigenstate thermalization. So for those who are familiar with eigenstate thermalization, what eigenstate thermalization says is that if you have simple operators in high-lying eigenstate, they look thermal up to exponential corrections. So what we have is that we can show that on eigenstates, the expectation values are thermal. That we can show. But in order to show that the corrections are exponentially suppressed, we need to work with a typical state in the microcanonical sliver. Okay, so and that's when we can actually show that the exponential suppression happens. So it's more precisely, this is microcanonical thermalization rather than eigenstate thermalization, which is a pity, because if you really wanted, if we could show eigenstate thermalization, we could really sort of hope and argue that this shows genuine chaos in the system, because it's usually taken as a kind of isomorphic to the existence of quantum chaos in the system. So, but this is harder because we have to really work with the actual normal modes, and normal modes, explicit normal modes, are complicated. So, yeah, so the Hartle-Hawking correlator is usually obtained by demanding smoothness of the horizon, and this is what corresponds to the the infalling observer's Kruskal vacuum. And so this is what I would call as some sort of a hint that the stretched horizon, at least in principle, may be able to capture some features of a smooth horizon, even though it's manifestly not smooth. Okay, if you think of it as a UV complete description, and which is the way I'm thinking about it. So what this is telling you is that in the effective field theory description, you can perceive smoothness. Effective field theory, we assume that it is in some sense coarse grained and so on and so forth. And so you get this smooth horizon, but in the microscopic description, it's actually not. There is no black hole interior in this picture. So as I said, it would have been more satisfying if we could do this without relying on typical states, even to show that the variance is suppressed. Because one of the reasons why I don't like typical states is because typical states, it's plausible the typical states are firewalls in ADS-CFT. I mean, I can say more about it if you like, but yeah. So to the extent that typical states are firewalls, it may not be the right setting to expect to see the smoothness of the horizon. So, I'm almost done. So, and my time is also out. So, in any event, together with our previous results, this means that the near horizon normal modes can reproduce, various thermal and quantum chaos-like characteristics, at least in the case of BTZ. we are trying to generalize it to higher dimensions, especially this 2-point function calculation. Yeah, so the one thing that I will kind of take away from here is that the exponential quasi-degeneracy in the compact directions near horizons which have when there is redshift in the picture, that's what gives rise to all of the things that we see. And the question is whether it can be used as a general mechanism for gravitational entropy. So let me also point out that the Ryu-Takenagi surfaces, which are what one uses in order to compute entanglement entropies in holographic theories, at least for spherical subregions in the boundary of ADS, these Ryu-Takenagi surfaces can be viewed as horizons of ADS-Rindler spaces. So they're also the calculation, the kind of calculation that we're talking about, can in principle work there as well. So for instance, in Rindler case, we can explicitly check it. ADS Rindler, it's a bit harder because the the wave equation is harder to solve, but I think it should be possible to do it. So I'll stop there. Thank you for your patience.
All right. Thanks, Chethan, for the wonderful talk. So I guess it's time for the question. So if anybody in the audience has any questions, like, please go ahead.
So thank you for the talk, Chethan.
Thank you.
So the question I have is, so for solving the equations that you want, so I'm sort of more at the beginning, not at like discussing your results yet. Which type of boundary conditions do you need to set up for, solving the scalar in the backgrounds?
So I'm demanding normalizability at the ADS boundary, and I'm demanding Dirichlet boundary conditions at the stretched horizon.
Okay, I see. And is that enough for?
That's not enough to fix the overall scale of the solution. But it is enough to fix it's enough to fix the normal modes.
Okay, very good. Okay, thank you.
Yeah, sure.
Do you have more questions? Do you have more questions for anybody?
Yeah, so I don't know whether I judged my audience correctly. I was kind of prepared it sort of more for a holography string theory crowd, I think, but hopefully I tried to make it a bit more general than.
It's all right. I think most of the audience
all right, great.
Yeah, do you have more questions from the audience? Please unmute yourself and go ahead and ask. All right, so if there are no more questions, so let's thank Chethan again for the wonderful talk.
Thank you very much.
And we'll see. Let's stop the recording now. Yeah. Okay.